All right, so the exam due today on Sunday is Chapter 5 homework questions. And this time the homework questions are not through Connect, through the publisher. It's a homework set that I made on Blackboard. You do have 3 attempts, just like with the McGraw-Hill homework. If you get any wrong, there's feedback to try to help you correct it for your following attempts. It's only 10 questions, I believe. Most of them are multiple choice. Also, the Chapter 5 discussion is going to be due Sunday as well. Please give me feedback on the homework questions if you like the Blackboard version that I made, if you prefer that over the McGraw-Hill. Because if you do, I'm going to continue making them via Blackboard. I've actually already made Chapter 6 and 7 homework quizzes that I can post as well. So, this information, it only really takes a day to explain. I have the PowerPoints up and I already have a video up working through some of the problems. So what I'm going to do today is I'm just going to talk about all of the laws, and then I posted in the supplemental material folder a practice worksheet, and it says Chapter 5, 6, and 7 homework. It's not a homework assignment that's due. This is just practice. There's even an answer key posted as well. So we're going to work through these problems on the board today. So let's start off looking at Boyle's law. So for all of these laws, it's about gases. So when we're talking about gases, the variables that are important are pressure, volume, temperature. Okay, so all of these laws will have one of those variables in it. Starting with Boyle's law, we have pressure and volume. Now notice we have pressure and volume on both sides of the equal sign. P1, V1, P2, V2. So what that means is there's going to be 2 different pressures and 2 different volumes. Now when we're measuring these, when we're using this equation, pressure, the units are usually in ATM, and the volume is usually in liters. Okay? It doesn't have to be though. The key here is that the units for pressure and volume, they just need to be the same. Because since pressure's on both sides of the equation and volume's on both sides, as long as they're in the same units, you can leave them in the same units. You don't need to convert. So for instance, if volume was in milliliters, well, as long as both V1 and V2 are in milliliters, you can leave it in milliliters. It doesn't have to be converted to liters. You just need to make sure they're in the same units. These are just the usual units that we see them in. For Boyle's law, we're going to see that pressure and volume are inversely proportional. That's what this means here. So if we're increasing the pressure, we're going to see the volume decrease. And you can kind of see that if you're trying to squish something, you're applying more pressure to it, squish a gas, so the volume inside the chamber that you're squishing is going to get smaller, less. So inversely proportional means if one goes up, the other goes down. All right, so for Charles' law is relating volume and temperature. So once again, volume and temperature are on both sides of the equation. For this one, temperature has to be in Kelvin, always. If it's in Celsius, you need to convert it to Kelvin. I know it's on both sides of the equation, just like with pressure and volume, and I said as long as they're in the same units, you can keep them. But that doesn't work with temperature. We can't leave it in Celsius, because Celsius is not an absolute scale. You can go into the negatives in Celsius. We have to convert it to Kelvin to have it in an absolute scale in order for this equation to work. So I have the conversion equation for converting to Kelvin, and we've done this before in a previous chapter. So to figure out Kelvin, you take whatever the degrees Celsius is and add 273 to it. And for this equation, we see volume and temperature are proportional. So when I say they're proportional, if one goes up, that means the other is going to go up. So if I increase the temperature, I'm going to increase the volume. The next equation that we're going to use is Avogadro's law. So we've talked about Avogadro actually in Chapter 4. We used Avogadro's number, which defined what a mole was, the 6.022 times 10 to the 23rd. So it shouldn't surprise you that Avogadro's law has moles in it. That's what this n variable is. So we have volume, which is usually measured in liters, but as long as it's the same on both sides, You don't need to convert to liters. And then the N value, that's moles. And that's always going to be in moles. It's not going to be in anything else, any other units. So this is the same, and by the same I mean volume and the amount of moles are proportional. So if the amount of moles goes up, what that means is we have more atoms. And more atoms are going to take up more volume. So if the moles go up, the volume goes up because the atom amount is increasing. More atoms are being added. Looking at the combined gas law, now we're including pressure, volume, and temperature. Okay? It's on both sides of the equation. So pressure and volume need to be in the same units. Whether that's ATM, torr, millimeters of mercury, or for volume, liters, milliliters, as long as it's the same units. Temperature does have to be in Kelvin. So converted if it's in Celsius. Now the last law that we're going to look at in this chapter is the ideal gas law. And for this one, notice we don't have any P1s, V1s, P2, V2. We only have one pressure, one volume, one molar amount, and one temperature. So since we only have one of each, the units matter. So pressure has to be in ATM for this one. Volume has to be in liters. The N amount, moles, temperature has to be in Kelvin. Now this R value we haven't seen before, and this is called the gas constant. So we're going to insert this number every time we use this equation. Now, the nice thing about this gas constant is it reminds you what units you need for the other variables. Liters for volume, ATM for pressure, moles for the N, and then Kelvin for the temperature. Oftentimes too, when we see this equation or other equations, they'll often be under STP conditions. And I talk about this in the PowerPoints. So what STP means is standard temperature pressure. So when they say the words STP in a question, they're giving you the temperature. They're saying it's 273 Kelvin, and they're giving you the pressure, saying that it is 1 ATM. So by saying STP, they give you two variables, just with those letters. So the only law that I didn't write on here, the last one you have, is a law of partial pressures, and that's just where you're adding some partial pressures together. And you'll see that one when we use it, I think on number 9 in this packet here. So I'm going to go ahead and erase these, and we're going to start by doing number 1. I see there's 2 number 1s. The first number 1 on that practice worksheet. So how I like to approach these, since there's so many different possible equations to use for them, is I like to make a list of the knowns and unknowns, and then look at my equation sheet and see which one's going to fit. So doing it systematically kind of helps you know where to start. So if I make a list of knowns and unknowns, what I'm going to do is I'm going to go through this question. It says calculate the pressure in ATM required to decompress a sample of helium gas from 3.5 liters at 1 ATM to 4.2 liters. So there's a whole bunch of numbers in there. So start by labeling them with the variables. So the first number I see is 3.5 liters. And to figure out what variable goes to that, you look at the units. Liters is a volume. So I'm going to label this as V. It says that 3.5 liters is at 1 ATM. To figure out what variable this is, you're looking at the units. ATM says that's a pressure. Then it says it's going to 4.2 liters. So my next number is 4.2 liters. So notice I have 2 volumes. So if I have 2 volumes, I need to label these to keep them separate. So this is going to be my V1, my P1. My second volume that I come across then will be my V2. In the very first part of the question, it says calculate the pressure. So pressure is what they're asking for. So that's my unknown, that's my question mark. So looking at these variables, I go to my set of equations and I see which one's going to fit. So which of the equations has a P1, a V1, a P2, and a V2? Boils law. So we're using this equation here. Now before you use it, look at what you're solving for, rearrange the equation. So P2 is what we're solving for. So what that means is I need to get P2 by itself. So in order to do that, I need to get rid of this V2, this volume. Right now I'm taking P2 and I'm multiplying it by V2. So to get rid of it, I would do the opposite operation. So since I'm multiplying to get rid of V2, what I'm going to do is divide. Because now I have V2 divided by V2. It cancels. But whatever I do to one side of the equation, I have to do to the other. So if I divided by V2 on this side, I also need to divide by V2 on that side. So over here it cancels. On the other side, it doesn't cancel. So rearranged, I have P2 is equal to P1 V1 over V2. So now it's rearranged to solve for my second pressure. So now I just plug in my numbers. I have 1 ATM for my P1, my V1 is 3.5, and then my V2 is 4.2. Calculating for me. 3.5 divided by 4.2. How many sig figs are we looking at in this one? I think it was 3. Yes. So 0.833. Now for the units, it's pressure, and it was an ATM. 0.833 ATM. So let's look at the next one. We're going to go through the same process. We're going to do our knowns and unknowns, and then we'll see what equation works, rearrange the equation, and solve. So the second number one, we have a balloon filled with helium gas at 1 ATM occupying 15.6 liters. What volume would the balloon occupy in the upper atmosphere at a pressure of 0.15? All right, so the first piece of information I see is 1 ATM. I know that that is a pressure. I also notice they give me more than one pressure, so I'm going to label the first pressure I see as P1. Now this P1, the pressure of 1 ATM, occupies 15.6 liters. So 15.6 liters. Units of liters tell me this is volume. More specifically, V1, because they're saying that balloon has a volume of 15.6 liters when it's at a pressure of 1 ATM. So what they're asking next is, okay, well what if the pressure changes? So my new pressure they give me, since that balloon floats away in the sky, is 0.150 ATM. So that's my new pressure. They're saying at that new pressure, what's going to be the new volume? What's happening to that balloon? Is it going to get bigger or is it going to get smaller? Is the volume going to increase or decrease? So you'll notice once again, same variables as the last equation, so we're using Boyle's law again. And we can actually predict what's going to happen to the volume because with Boyle's law we said that pressure was inversely proportional to the volume. So if the pressure is increasing, the volume is going to decrease. If the pressure is decreasing, the volume is going to increase. So we can predict what's going to happen based off that. Let's go ahead and rearrange this equation. We're solving for volume this time. So we want the V2 by itself. So we want to get rid of this P2. To get rid of it, we're going to divide. Whatever we do to one side, we have to do to the other. It's going to make my P2 cancel on that side, and I get my rearranged equation. So let's plug in. My P1 is 1 ATM. My V1 is 15.6. And then my P2 is 0.150. So we have 15.6 divided by 0.150. 104 units. Okay, so this is my V2. It's a volume. Volume is in liters, so we keep it in liters. So the volume increased a lot. That balloon probably popped, I'm guessing, because it went from 15.6 up to 104. Well, let's see if this checks out. Pressure and volume are inversely proportional. We just said the volume went up. So if the volume went up, that means it's because the pressure went down. So let's check. Did the pressure go down? Yes, it did. It went down from 1 down to 0.15. So it went down a lot. That's why the volume increased so much. All right, let's do the next one. So we have a balloon again. This time, they have the balloon measuring at 1.45 liters, liters being a volume. That balloon at that volume is at 280 Kelvin. So the temperature of that balloon, or of the atmosphere that balloon is in anyway, is 280 Kelvin. Now they give us a second temperature next of 306. So I'm going to label these V1 and T1. And then the next temperature they give me will be T2, so I can keep them separate. And the question asks, what is its new volume? So what is its V2? So now we have volume and temperature. And the equation that relates volume and temperature is Charles' law, where you have V1 T1 over V2 T2. Now for this one, the temperature has to be in Kelvin, and it already is, so no conversion necessary. So now what I'm going to do is I'm going to rearrange the equation to solve for volume. So now this time I'm dividing by my temperature. To get rid of it, I'm going to do the opposite of division, which is multiplication. So I'm going to multiply by T2. Whatever I do to one side, I have to do to the other. So over here, T2 is going to cancel. I get T2 V1 over T1. There's my new equation. Now I plug in. So I have 306 for my T2. My V1 is 1.45. My T1 is 280. So let's see what happens to the volume. Sig figs, we're looking at 3, so I have 1.58. It is a volume, and it's in liters. So 1.58 liters. So with this, Charles' law, volume and temperature were proportional, meaning if one goes up, the other goes up. If one goes down, the other goes down. So in this case, we had the temperature going from 280 up to 306. So the temperature went up, so we would expect the volume to go up. Okay, did it? It went from 145, yes, up to 1.58. So that answer makes sense. It's kind of nice to know the trends of the equation itself because it kind of gives you a double check for your answers. Make sure that they're following the trend kind of helps prove that you did the problem correctly. All right, so for number 3, I'm just going to do one of them. There's an A, B, and C, but they're all the same calculation, so I'm just going to show one. So we have a sample of nitrogen gas, has a volume of, so it specifically tells us that the number following is a volume, If it didn't say that, we would know it because of the fact the units are liters. So that nitrogen gas has a volume of 3 liters at 25 degrees Celsius, and that's going to be a temperature. What volume will it occupy at each of the following temperatures if the pressure is constant? So when it says the pressure is constant, what that means is you don't need the pressure to solve. Okay, you just need volume and temperature. So I'm going to do A, and the temperature in A is 100 degrees Celsius. And they're asking what is going to be the new volume at that temperature. So you would do this problem for each temperature, just changing the T2. So for B, the T2 would be 150. For part C, the T2 would be 0. But the calculation itself is the same. Now notice I'm solving for V2, so I've done that already. I have the rearranged equation over here, so I'm just going to use this same rearranged equation. The difference with this problem, though, is my temperature, it's in Celsius. It needs to be in Kelvin in order to plug it into that equation. You can't leave it in Celsius. So I'm going to convert these by adding 273. So I get 298 Kelvin for my T1 and 373 Kelvin for my T2. Now I'm going to use the rearranged equation that I have over there, T2, V1 over T1, and plug in. So I have T2 is 373, V1 is 3 liters, and my T1 is 298. .373 times 3 divided by 298. 3 sig figs again, so 3.76 is a volume, and it's liters. So temperature went up, so we expect the volume to go up. So that answer makes sense. So now let's move on to number 4. Number 4, we have the temperature outside is 308 Kelvin. The car's tires have a pressure of 1.19 atm. So let's start writing this down. 308 Kelvin is a temperature. The pressure, it says, is 1.19 atm. And it says, what is the pressure when the temperature increases? So since I have a second pressure and a second temperature, I'm going to label my first set T1, P1. And then my second temperature of 290 will be T2. They're asking to solve for pressure, P2. Now in this one, it says volume is constant. So what that means is you don't need the volume. So looking at my equations, I need an equation that has temperature and pressure. The only equation that has both is the combined gas law. That's P1 V1 over T1 is equal to P2 V2 over T2. Now, using this equation, it has volume in it, but they didn't give me any volume variables, amounts. But what they did say was the volume is kept constant. These are tires. So if the volume's kept constant, that means I don't need it. It stays the same on both sides of the equation, so I can cross out that variable because it's the same on both sides. So this makes my equation become just P1 over T1 is equal to P2 over T2. My temperature is already in Kelvin, so that's good. The pressure doesn't matter as long as the units are going to be the same. So let's go ahead and rearrange this equation. We're trying to solve for P2, correct? Yes. So I need T2 to get on the other side of the equation. So to do that, I multiply by T2. Cancels out on this side, T2 divided by T2 cancels out. And my equation becomes T2 times P1 divided by T1. So T2, my temperature of 290. P1 is 1.19 ATM. T1 is 308. So let's see what my new pressure is, and then we'll talk about if it makes sense or not. So we are looking at just two sig figs, I believe. 1.1. Units, pressure, ATM. Okay, so what's happening? We're talking about car tires. The temperature outside is decreasing. So if the temperature is decreasing outside, what's going to happen is we should see the pressure decrease. And you probably noticed this in winter, maybe recently even with the temperature dropping, that you had the light on your car come on or you needed to add more air to your tires. That's because the temperature is decreasing. When the temperature decreases outside, that makes the gas atoms in your tires not move as fast. And when they're not moving as fast, they're not hitting the sides of the container as often. So if they're not hitting the sides of the container, that means the pressure's going down. So if the pressure goes down, which it did, it went from 1.19 down to 1.10 essentially, the pressure goes down, you'll need to add more air to the tires to get the pressure to increase, more atoms. All right, let's do one more and then we'll do the rest on the next video for Friday. This one's usually a hard one for most people because by realizing it's a tire and the volume's kept constant, you need to know you can just cancel out that variable. So that's kind of a tricky one. So let's look at number 5. Number 5 has cyclopropane used as a general anesthetic. So if a sample was stored at 2 liters, so volume 2 liters, and the container is at 10 ATM. Remember ATM, the units tell you that that's a pressure, and 25 degrees Celsius. Degrees Celsius is a temperature. Now then they're saying this gas is going to be transferred to a different container with a different volume and a different pressure. So that means they're going to give us a new volume, a new pressure. So these 3 are all going to be labeled B1, P1, T1. Now the second set will be B2, P2, T2. So my new volume, the new container is 5 liters. The new pressure is 5 ATM. And the resulting temperature is the question mark. Now, just check and make sure the units are the same, consistent. For volume, liters, liters, we're good there. Pressure, ATM, ATM, good there. Temperature, degrees Celsius, no, can't have it. So we're going to add 273 to it to get it in Kelvin. It's going to be 298. And then once I solve for T2, that units will come out in Kelvin. All right, so let's look at our equations. We need one that has all 3 variables. So if it has all 3 variables on both sides of the equation, we're once again looking at the combined gas law, but this time the pressure is not held constant. So, or the volume is not held constant, excuse me, so we keep that V variable in there because we have values for the V's. So let's rearrange this to solve for T2. This is one of the hardest ones to rearrange, is why I like to show this one. I need to get T2 by itself. Well, it's in the denominator. So my first step is to get T2 up in the numerator. So to do that, I'm going to multiply by T2. So I get T2 times this whole guy, and then cancels over here, T2 over T2. So now I have this. Okay, T2 is still not by itself, but it's up in the numerator, and that's where I need it to be. So what I need to do is I need to get rid of this entire thing, P1, V1 over T1. So to get rid of that, what I'm going to do is I'm going to multiply by the reciprocal. So if you don't know what a reciprocal is, it's this fraction flipped. Okay, so let's kind of spread this out a little bit. Just spreading it out to make room for my reciprocal. So if I want to get rid of this, I'm going to flip this fraction. So I'm going to put the T1 on top, and then the P1 and the V1 on bottom. So this is my reciprocal, is what it's called. And if I multiply by that reciprocal, what I'm doing is I'm getting it so that the variables are on opposite sides of the horizontal line so that these variables all cancel. Okay, but since I multiplied by this reciprocal on this side, I have to do the same. Right? Whatever I do to one side of the equation, I have to do to the other. So I'm going to put that same reciprocal, the T1 over P1, V1, over here as well. So on this side of the equation, it's all going to cancel because they're on opposite sides of the horizontal line, so they all cancel each other out, which is what I wanted because I need T2 by itself. But on this side, now I can combine all this. So in the numerator, I'm going to have P2, V2, and T1, all multiplied by each other. And then in the denominator, I'm going to have P1 and V1. So now, plug in our variables. P2, 5 ATM. V2, 5 liters. T1, and we're using the Kelvin amount, 298. So that's what I have on my top. P2, V2, T1. On the bottom, I want P1 and V1. So 10 times 2. So multiply by what's on top, 5 times 5 times 298. Divide by what's on the bottom, 10 times 2. And I get 372.5, but I only want 3 sig figs, so I'm going to round that up to 373. The units, it's a temperature, needs to be in Kelvin. Oops, 373. All right, so that takes care of number 5. So Friday's video, I'll finish doing the rest of the problems on this practice worksheet. So 6, 7, 8, and 9. 4 more problems left, and that will conclude chapter 5.